In this example, we've got a region enclosed by y equals x minus 1, y equals 0, and x equals 3, and it's being rotated around the x-axis. And so I'm going to sketch the picture. And what I would encourage you to do is spend some time coming up with the integral yourself. See if you can solve it yourself. So pause the video and do this, and then compare your work. You need the practice with these kinds of things, just like you would get in class. So go ahead and pause the video, see what you can come up with. Now, in this case, our axis of rotation is the x-axis, and big R, I'll do in red, is the distance from the outside of the curve to the axis, which is right here. Big R, in this case, is the distance x minus 1, and there is no little r because there's no smaller part, there's no portion coming out. And we can see that this goes from 1 to 3, and we'll be integrating the area of a circle, pi times x minus 1 squared dx. Again, notice that our object has circles that are oriented horizontally to one another, and so everything is in terms of x. When we integrate this, we would end up with 1/3 times x minus 1 cubed times pi, and taking my upper limit of integration, 3, that'll be 8/3 minus 0. So the volume of my object is 8 pi thirds units cubed. In the next problem, we're looking at the exact same scenario shape-wise, but our axis is going to change. In this case, it'll change to the line y equals 2. So here's the picture. And our object's going to look something like this, again with horizontal circles, but it's kind of got this cone that's being taken out the back of it. So in this case, big R is from y equals 0 to 2, so big R in this case is 2. Little r in blue is this piece right here, and that piece is 2 minus this portion right here, which is x minus 2, which means that little r is 2 minus, x minus 1, or little r is 2, 3 minus x. And based on that expression, we can set up our integral. It'll be pi times, still running from 1 to 3. Big R in this case is 2, so we'll have 2 squared minus 3 minus x squared dx. Right? Our circles are oriented horizontally, they're stacked horizontally, so everything is in terms of x, at least the way we're looking at it. If we clean this up, we're going from 1 to 3, but this will be 4 minus 9 minus 6x plus x squared dx. And taking this one step further, this will be negative x squared plus 6x minus 5 dx. When we integrate this, we'll end up with negative 1/3 x cubed plus 3x squared minus 5x from 1 to 3. And now it's time to substitute in our limits of integration. First we'll substitute in 3, so it'll be negative 9 plus 27 minus 15 minus our lower limit of integration is 1, so this will give us negative 1/3 plus 3 minus 5. And cleaning all of this up, we end up with we end up with 16 pi thirds units cubed for our volume. Example number 3, again it's the same situation, with the only thing that has changed being the axis of rotation. This time our axis will be the line y equals 3. Again, I would encourage you, pause it, draw the picture, set it up yourself. So here's the picture. We're going to have an object that looks something like this, with maybe more of a kind of a cone in the middle of it, but it doesn't come to a point. Again, we'll set everything up. Big R is the distance from the outside of our curve to the axis of rotation. So in this case, big R is 3. Little r, we'll do in blue. It's this distance right here. And that distance is 3 minus this piece right here, which is x minus 1. So little r must be 3 minus x minus 1, or cleaning it up, little r in this case will be 4 minus x. So not much has changed about our integral, except for a couple of things regarding the integrand. It'll still be pi times the integral from 1 to 3 of big R, 3 squared, minus little r, 4 minus x squared dx. Now we'll just start cleaning up before we integrate. So we'll have 1 to 3 of 9 minus 16 minus 8x plus x squared dx, which cleans up to the integral from 1 to 3 of, that's that, negative x squared plus 8x minus 7 dx. Integrating, we end up with pi times negative 1/3 x cubed plus 4x squared minus 7x from 1 to 3. Now it's time to substitute. Substituting in 3 again, this will be negative 9 plus 36 minus 21, minus, substituting in 1, this will be negative 1/3 plus 4 minus 7, and cleaning it up, we end up with 28 pi thirds units cubed. I'm going to clear this off and we'll deal with the exact same problem, exact same setup, except this time we'll revolve around something else. This time we're taking that same shape but rotating it around the y-axis. So that means that our circles will be oriented vertical to one another. So our object's going to look something like this. And this object is going to have a center in it that's also slanted downwards. In fact, won't be doing that. It's going to be doing something more like this. So again, it's just a cone coming out the top. And there'll be a smaller circle at the bottom than there will be at the top. So our circles are stacked vertically, so we'd like to have everything in terms of y. So one thing that's true is that our object will go from 0 to 2, right? 0 is the bottom, and up at y equals 2 is the top. Let's look for big R. Big R is the distance from the axis to the outside, which in this case is 2. Little r is the distance from the axis to the inner, which is just this piece right here. And in terms of y, so this is y equals x minus 1, But if we solve this for x, we get x equals y plus 1. So little r, in this case, is y plus 1. So our integral then, from 0 to 2, will be 2 squared minus y plus 1 squared dy. And now, once we've set up the integral, it's just smooth sailing, just cleaning up, right? So this is 4 minus y squared plus 2y plus 1 dy, which is, let's see, negative y squared minus 2y plus 3 dy. Integrating, we end up with negative 1/3 y cubed minus y squared plus 3y. And this is from 0 to 2. Substituting in 2, we end up with negative 8/3 minus 4 plus 6. Substituting in 0, we get minus 0. And cleaning all of this up, we end up with, I'd like to say I did this on purpose, but I didn't. Some of you probably saw my mistake early on. Big R is not 2, because big R is 3. And that affects everything. So if you caught it, good for you. Apologies for messing up the first time. This should be 3, which makes this 9, which means that this would be 8, which means this would be 8y, which means this will be 16, and now we have something that makes sense. We'll end up with a volume of 28 pi over 3. So I'd like to say that I did that on purpose, but I didn't. I just messed up, and luckily I was able to find my mistake quickly, as far as you know. Moving on, we'll deal with the same situation, but a different axis of rotation. Again, we just need to practice a lot, as I just made evident. It's easy to make a small mistake. The axis of rotation is x equals 3 in this case. So I'll draw the picture, you set it up, see what you can do, pause the video, but practice, practice, practice. Here's the picture. So our object's going to look like an upside down cone, or a circular pyramid, I suppose. Let's find big R and not make a mistake this time. Big R is the distance from the outside to the axis of rotation. And this piece here, big R, is a combination of a couple things. It's 3 minus this part, which we know from the last problem is y plus 1, which means that big R is 3 minus y plus 1. Or cleaning it up, it's 2 minus y. There is no little r because there's no hole in this in any way, shape, or form. So we can set up our integral. Everything will be in terms of y. So this will be pi from 0 to 2 of 2 minus y squared dy. I'll integrate this by undoing the chain rule. So this will be pi times, let's see, it would have been 2 minus y cubed times negative 1 from 0 to 2. No, times negative 1/3. That's better. Again, if you weren't sure about what you have for an integral, you can always take the derivative and you should get back to where you started. Now that we've integrated this, we can evaluate by first substituting in 2. So when I substitute in 2, I'll have 0 cubed, which is 0, times negative 1/3 is also 0, minus, when I substitute in 0, 2 minus 0 is 2, cubed is 8, so it'll be negative 8/3. And combining everything, my volume is 8 pi over 3 units cubed because it's a volume. We'll look at one more here for our second example, and again we're just doing lots of examples as part of this. The axis of rotation will be the line x equals 5. So go ahead and pause it and see if you can set it up. My object is going to look something like this, and it's vertically organized circles, so everything will be in terms of y. First thing I know is I'll be integrating pi from 0 to 2. Now I'll identify big R, which again is from the outside of my curve to my axis, and that piece is some combination of 5 minus this portion right here, which we know from previous work is y plus 1, which means that big R must be 5 minus y plus 1, or it's 4 minus y. Little r is, I'll do in blue, is the distance from the inside of my curve to the axis. This is from 3 to 5, so little r has a value of 2. Setting this up then, I'll have 4 minus y squared minus 2 squared dy. Cleaning this up, pi from 0 to 2, this will be 16 minus 8y plus y squared minus 4 dy, or cleaning up a little more, this will be y squared minus 8y plus 12 dy. Integrating, we'll end up with 1/3 y cubed minus 4y squared plus 12y from 0 to 2. I'm really happy that one of the limits is 0 because everything will cancel out, but when I substitute in 2, we get 8/3 minus 16 plus 24 and minus 0 when I substitute in 0. So altogether my volume is 32 pi over 3 units cubed. There's a completion of example 2, and again, a lot of practice. This is a super important concept.